Hey, good afternoon, everyone. I wanted to do our warm-up here. I know this is from section 3.5 before we get into 4.1. This won't take much time, but it'll be neat just coming off the box plots that we did in section 3.5. I put 2 box plots so we can compare and talk about them. I'm just going to make some statements, and I was wondering if you, the class, could just tell me, true or false in my statement in reference to these 2 box plots, all right? So, now if you can't justify from the information given, then go with false. You can say, hey, false, I don't have enough information to tell me that from what's provided here on the board. So, here's my first statement. Ready? True or false? The median of box plot A is greater than the median of box plot B.
True.
What do y'all think? True or false? I'll repeat it too. The median of box plot A is greater than the median of box plot B. True. Very good. It's true. The median's right there, right? 70. There's the median, and the median of box plot B is the 30. Everyone know how to find that median? And you can once you have this here, you can label it. You can write stuff on your box plots like, hey, that's Q1, that's median, that's Q3, that's Q1, Q3. But the first statement, we're coming out with true, right? All right. So very good. Here's my next one. 25% of the data in box plot A, 25% of the data in box plot A is less than 50. True or false?
True.
Good job. He says true. He says true. Very good. That is correct. Remember percentages? That's the beauty of the box plot. It tells us about percentages. So even in this drawing here, I bet a lot of you might have already done this, but it wouldn't be a bad idea to just go into this thing. Hey, well, 25% of this data is here. Then 25% is in here, and 25% is in here, and 25% is from 80 to 90. And those add up to 100%, right? And then the same thing here, you get 25%, 25%, 25%, and that long whisker from 50 to 90. Cool? Hey, true or false, there's no outliers.
True.
True, when you don't see any stars anywhere, right? There's little asterisks. There's none drawn on the board. So there are no outliers. Very good. Here's my next one. The range of box plot A is equal to the range of box plot B.
True.
Now the range, that has a definition. It's max minus min. Everyone's saying true. So the max is 90, the min was 10. 90 minus 10 is 80. In this group, 90 minus 10 is 80. The ranges are equal. True? All right. I try this one. The inner quartile range of box plot A is equal to the inner quartile range of box plot B.
True.
Or false?
True.
Oh, you all are quick. They're saying true. Let's look at that. So if you're like, how'd they get that? The inner quartile range is the 80 minus 50, which is 30. And over here, the inner quartile range is the 50 minus 20, which is also equal to 30. So far, everything's been true, right? Excellent. I got another one. I want to go back to the percentages. 75% of the data in box plot B is less than 50.
Sure. 75%. Can you repeat that?
Yeah, I'll repeat that. 75% of the data in box plot B, 75% is less than 50. True. Yeah, look, 25%, 25%. So 75%, if these were scores on a test, let's say, then yes. 75% of the students in class B scored a 50 or less. Wow, yeah, that's what we're saying. That's what we can see in a box plot. So all these statements, I'll do percentages again. Roughly, let's see. Yeah, roughly 75% of the, if these are students in group B scored less than roughly 75% of the students in group A.
True.
Yeah, can you see that? Look, 75% of the students in group B scored less than 75% of the students in group A. That'd be a true statement. So everything I've said so far is true, right? All right, now, you get out your highlighter. Ready? Here we go. True or false? Group A and Group B have the same amount of data.
Same amount. It cannot be determined.
Yeah, I'm gonna say this again. Group A, because we know this represents data, right? It's a distribution of the data, it's a nice image, tells us about, and I'm making a statement, true or false. Group A and Group B have the same amount of data. And when I'm talking about data, I'm talking about like, think of that word sample size, right? They both have the same sample size in both of these. And we're sitting there going, no, there's not enough information for that.
Yeah.
We're gonna have to say false, because we can't justify it, all right? I mean, that's what's hidden in the box plot. I want you to highlight that. Go, we're gonna have to say, cannot justify that. This could be representing 1,000 students, or this might only be representing 30 students, right? Oh, Gary, go ahead.
I just thought that one class was smarter than the other.
That's a good observation. He's like, man, which class did a lot better? These are scores. Which one, Gary? Did a lot better. Yeah, he's like, Group A. Did a lot better in Group A. But anyway, in this case, what's the one thing of all those statements I made, we're like, hey, we can't justify that. This idea I say, hey, I'm looking at these because they look similar in terms of box plots, in terms of the ranges were equal. And then you go, well, then they're representing the same amount of data. We're like, we don't have enough information for that, right? The amount of data, the number of data in here, the sample size. This might be, it's not written anywhere, but this might be sample size 987 students. And this might be a sample size of 62 students, right? And this is what we get. So that's the one thing we don't see in the box plot. You know, it wouldn't be a bad idea if you ever produce one of these off to the side to show your sample size, right? N equals 52 students or something like that. So does everyone go with that? That's the one thing I want to point out. You go, okay, we don't have enough information for that. We can't justify that. Awesome. Hey, one more. Data set, true or false? Data set B is skewed to the right. That's true. Skewed to the right. Everyone agree? Cool. Excellent. And you got box plots down. All right, so we're going to get into scatter diagrams and correlation. I made a table over here. I want to tell you where I grabbed this table. I took it from page 191 from your textbook. So if you just wanted to know where this was in your textbook, I took this table right here. It's a table on page 191. The person who did this study was actually a student from Joliet Junior College. Who did this study. This involved golfers. He looked at the relation between club head speed of a golf club. So a golfer, I'm a lefty everyone, but you know, the golfer, and they hit the golf ball, and the speed at which that golf club is hitting that golf ball in relation to the distance that the ball traveled. And a lot of you probably thinking logically, yeah, the harder you hit the ball, in terms of distance, the longer, the further the ball should go, right? That was his idea as well. This individual's like, I'm gonna look at that, and I'm gonna see if there is a linear relationship. So that's what this section's all about. I know it's got scatter plots and correlation, but in section 4.1 and 4.2, 4.2 gets into linear regression. We're trying to see, is there possibly a linear relationship between these variables and these over here. So this is called bivariate data. So I'm going to put that down, that word. In chapter 4, we're turning to something new. We didn't see this before. We're looking at bivariate data. What does that mean? Oh, we got two columns, that's all. And they're these paired data. That 100 miles per hour goes with the 257 yards. That is an individual. Perhaps that's Bob, right? That's Bob. Or maybe this is Tiger Woods here. That's Phil Mickelson there, maybe, right? I know. So that's what we're talking about, bivariate data.
So is there one dependent, other one independent in this?
Excellent. That's exactly what's going on. And just like you did in an algebra class, outstanding, we consider this first column always the x,
Okay.
and then y will be dependent on x. So yeah, when you look in the book, you see two columns, you go, can I always think of that left column as the x and the right column as the y in terms of variables? Absolutely. You know, like these are my x variables, these are my y variables. And y is always dependent on what? X. Now there's other words we use in statistics, so I'm going to write them down. This right here, this is called the explanatory variable. The explanatory variable. The explanatory variable. All right, so club head speed of the ball in miles per hour is the explanatory variable. This responds to that. Art, you said dependent, so I'm gonna use, it's the response variable. This is the response variable. Yeah, that makes sense. It responds to the club speed, how far the ball goes. Yeah, okay. Hey, in some studies, I've seen people actually interchange these. Think, wait, I can make this the x and this y. Sometimes you can't. I do want to point out, it is possible to do that. All right. So the first thing we're going to do, Aaron, we're going to take this data here, and we're going to make what's called a scatter diagram or a scatter plot. I bet you've heard of that before, right? We're going to plot these points. We're going to plot them all, and it's just going to look like a bunch of dots, right? Well, let's do it. Let's do it together. We'll make a scatter plot. And later on, we can use the technology to do this as well. So x-axis, y-axis. All right, here's my y-axis. There's my x-axis. We can label this. This is what? What's x? Speed. You want to put miles per hour? What's along this y-axis? The distance. Here, all right, distance. Sideways. Distance. All right. And we'll put some tick marks. We'll make some dots, right? All right, now, I don't have to start at 0, do I?
No.
What? Look in there. Check the club head speed. What's the lowest speed you see?
100.
Yeah,
99.
they call this the scope of data. And here's my scope of data. I've got from 99 to, what's the highest it got to? So as long as I make my tick marks, I can start right here at 99. I'll go by ones. 100, 101, 102, 103, 104, a little bit farther, 105. That's as far as I have to go to produce this scatter diagram or this scatter plot. Now, look at the distance. What's the lowest? 258?
That's 257.
Ah, this is even lower. Thanks, everyone. Which one's higher? I mean, the highest. So when I'm going to try to make this y, I'm going to scale. Low is around 257, high is around 277. How about I start at a tick mark right here at 255? And then I could go by fives? Does that sound good? I'll just make each tick mark go by fives. I don't have to go by ones, right? All right, so 255, 260, 265, 270, 275. Go a little bit further up here and go 280. And that way I hit, and I can plot all these. So this is 260, 265, 270, 275. These are my distances. These are in yards. And as we do this, it's always good to do this by hand first, right? And we're like, well, I want to make this with the calculator or with Microsoft Excel, the spreadsheet. You absolutely can. All right. So what's the next step? We plot these. Everyone okay with plotting these ordered pairs or XY coordinates? All right, 100, 257. Doesn't have to be perfect. We'll just estimate it. For this one, I'll go over 100 up to 257. It's about here. Make a dot. 102, 264, about right there. 103, 274, about here. And this study was actually done. 101, 266, about right there. 105, 277, about there. 100, 263. Oh, so this is interesting. Two people had club speeds of 100 miles per hour. So those dots are on top of each other. This doesn't have to be like a function. Remember the function test, vertical line test in algebra? It's like, no, it's a scatter plot. Scatter diagram. This can happen. I got two more. 99, 258. It's about right there. And 105, 275. All right, that's about right there. Just estimating. Making all these dots. I try to make my dots big so everyone can see them. Does that work? Scatter plot. Scatter diagram. Boom. And we'll discuss this. We'll talk about this. Really in 4.2, we're like, man, is there a linear relation between these two variables? Between club head speed and distance. Is it linear? By linear, I'm talking a straight line, right? It's never going to be a perfectly straight line, true? But if the dots are pretty tight together, it's all going up like this. You know, we might say, hey, there appears to be a linear relation here. We can use words like strong and stuff like that. There appears to be perhaps a strong linear relation. So that's where we're going with right now, okay? That's what we're going to do right now, is talk about correlation. Everyone okay with the scatter plot? Awesome. So now let's get into that discussion. Like, how can we determine whether or not there's a linear relation possibly going on here, all right? Well, everyone, there's something called the linear correlation coefficient, and it has a math formula. I was wondering if anybody right now still has that formula sheet on them.
Yeah.
If you don't, it's okay, I'm going to put it on the board for you. I want the whole time you go, oh, there's a math formula for this, okay? And you go, what is it called? It's called the linear correlation coefficient. And you bet it has a formula. It's represented by letter R, lowercase r. So new symbol for us, right? We know S is sample standard deviation. X bar means sample mean. Here's R, and it represents, with bivariate data, the linear correlation
Is
coefficient.
that for sample or population?
This would be for a sample.
Sample, okay.
That's right. And hey, I'm talking about a sample, everyone. Over here, you see all these numbers? That's like a golfer, like Tiger Woods, Phil Mickelson, etc. So how many golfers were there? 1, 2, 3, 4, 5, 6, 7, 8. So over here, in terms of this problem right here, I just want to point out our n equals 8. Sample size does equal. I didn't want you to think you go, do I have to put 16? Because there's 2 columns. No. We're talking about a sample size of 8 with these data being paired. Over there. All right. All right, what's this formula? 1 over n minus 1. Sigma, doesn't that mean summation? And you got the, got to take each one of the data values, subtract the sample mean, and I'm making a product here, a multiplication. Over standard deviation of y. I'll read this to you. I mean, this is the formula. As you can see, it's pretty intense. You're like, whoa. Because we all know how long it takes just to get the standard deviation of, say, the x-axis by hand. Wouldn't that take a while? We noticed, we did it last, we're like, just to get the standard deviation of x would take a while. Then I have to get the standard deviation of y. We all know how to get an x bar, right? The mean of the x's. Remember, these are the x's. These are the y's. And what I would do is, I would sum all the products. But x sub I represents each one of those x values in there. And y sub I represents each one of those y values. So everyone, if you would like to do this by hand, it'd be, you'd be encouraged to make a table to keep this organized and do all this. But you might find yourself just doing it with a calculator. It might take you up to 15 minutes, right? Wouldn't this take a while? So is everyone okay? We're going to use technology to do this. Absolutely. More important than the tedious calculations, we understand how we put all that stuff in there and make a table is understanding what does this mean, interpretation. All right? So we will use technology to do this. By the way, 1 over n minus 1, in this case, that's degrees of freedom. So we're saying it's 1 over 7 because we're big golfers. So we'll find this. So I want to talk about this R value. Let's get into what does it mean. All right, so the R value, what goes on with this thing? The first thing is it only can be numbers between -1 and 1. That's the first thing I want you to know. So I'm going to write that on the board, if you understand the notation for algebra. R, the highest R can be is what?
1.
1. What's the lowest R can be?
-1.
And you go, what does this R mean? Well, what's it called? It's called the linear correlation coefficient. You go, what does it tell us? It's going to tell us the strength of the linear relation in a scatter plot. It's going to tell us the strength. So what does 1.0 mean? I'm going to give you some pictures to give you some ideas.
It's going to tell the strength of what, Professor?
What's that?
It's going to tell you the strength of what?
Oh! Let me repeat that. This number, it's going to be a value, and it indicates the strength of the linear relation.
Okay.
We'll get a number. We're gonna be able to look at these numbers and go, oh man, there appears to be maybe a strong or weak linear relation.
Okay.
So that's what it's measuring for us. This would be R equal to 1.0. Now, everyone, do you notice my dots are perfectly in a straight line?
Uh-huh.
And do you remember the word slope?
Yep.
Can you see it's rising from left to right? That's why it's a positive one. But do you ever get data that really does that in real life? Oh, come on, look at this is what we get, right? We get scatter plots. They're scattered all over the place. But if this really happened, we're talking, okay,
Why?
perfect, you know? Extremely strong linear relation, right? The best. And by the way, what if the dots went like this in a perfect straight line and they came down like this?
-1?
You got it. So I want to put that. If you want to put -1.0 for emphasis, you can. Like 1.0 and -1.0. They're perfect. Perfectly straight. Those are the extremes. So now I'm going to do something like this. And because these are tight. I mean, these are grouped together very tightly and they're going up like this. So what would dots that maybe went like this, they were really close together. It's all going up in a straight line like that, it appears.
0.9.
Yeah, I'm going to put that down. And I'm just making this up. But they would give it an R value of approximately 0.9. And we can interpret that as a strong linear relation. Cool? Hey, what if they were really tight?
Negative.
They did. But they were going down, they were really tight. Maybe R would be about -0.9.
So,
Still strong though, right?
but
So this would be a strong linear relationship as well. The only thing is, positive versus what?
negative.
Negative. So if you want to, I'll go back in here, I said strong linear relation. In your notes, you can put the word positive before the word linear. But the word I'm going to put really big is linear. That's the most important word. Because that's what we're looking at. That's what we're examining. Is there possibly some linear relation between the two variables? If you want to say relationship, that's fine too. All right? That's what we're talking about when we're talking about correlation. Is there a linear relation? Right? Hey, and as I go through all this, everyone, will you remember one thing? Just because perhaps in the end we see, a correlation, correlation does not imply that you have causation. Will you remember that? Unfortunately, people do that in this world too often. They see like, I see a correlation. So that means this must cause this. I see a correlation between drinking coffee and this. Oh, then I guess drinking coffee is going to, cause cancer, right? You follow me.
It's a psychological thing too.
Yeah, exactly.
Psychology.
Exactly. Very good. So correlation does not what? Necessarily imply causation. Right. But it's interesting when you see some type of correlation. All right. So 1.0, -1.0, 0.9, -0.9. I'm making all these images on the board. Everyone, the author did a great job with this. If you want to look at it, if you have your book right now, go to page 194. His pictures are going to be a lot better than mine. But I'll keep going with this. All right? I'll keep going with this. I want to do a couple more images for you. So if you're like, where would I see some representations of this? Oh, page 194 has this stuff. Okay? So the next one I'm going to do is moderate. So I think I'll go over here on what if you had dots that were, they're a little spread out, right? Like this.
Moderate relationship.
Yeah, but you can still see, oh my gosh, it looks like it is going up in a straight line, perhaps. They're just scattered about. Maybe this, you'll get a moderate linear relation. And that might be like an R value of perhaps 0.4. And the author did a good job of just showing an image of this. And when you'll see that, and letter C, he's got R equal to 0.4, and he's got some dots that are just not as tight as these, but spread out. Okay? And then what would R equal to -0.4 look like?
Same thing.
Same thing, but
Different.
going down. And finally, I thought I would get to this. Way up here. What if you get this? Oh, from Charles.
No relation.
And so you get this after you do some study. And you get the dots all over the place. And you're like, there does not appear to be any linear relation, right? What do you think R is going to be very close to?
0.
Excellent. So on this, I'm going to write R is roughly, I'll just do that squiggle, R is going to be close to 0, maybe like 0.03 or 0.08 or negative 0.05. But there just appears to be no linear relation. Cool?
Mm-hmm.
Awesome. And when you might say, hey, I'm going to do a study, and I want to know which value would be like helpful and let me know if I do perhaps have a linear relation or not. This will be fine. Now, if you notice when you do your problem, and you get an R value of roughly, you get your R value of 0.8, 0.9, feel free to use the word strong. If you get an R value near like 0.4, 0.5, feel free to use the word what? Moderate. Or if you get an R value that's like very, very close to 0, you could say no linear relation, or feel free to use the word weak. Feel free to use the word weak, like there appears to be a weak linear relation. Okay? Now, do you have your textbook? Don't worry if you don't have it with you right now, but there is a table on this thing that pulls out in the back. All right? It's table 2. And I'll just hold it up for everyone, but I'll keep it attached to my book because you might do the same thing, because you might be saying, I'm going to sell this book, so I'm not going to pull this out. I might sell this book when the class is over. This is called the critical values for the correlation coefficient. That's what it's called. And what it has in there, critical values for the correlation coefficient, for different sample sizes, it has an R value listed. And as long as you get an R value that's going to be higher than that in your positive relationship, then you could say, oh, I'm good to go with this problem. There appears to be a linear relation. Because with my sample, I'll give you an example. The cutoff for a sample size of 9, everyone, is an R value of 0.666. So if you get a sample size of 9, 0.666, you'd be like, okay, I got an R value higher than that. There appears to be a strong linear relation. Anybody looking at this table right now?
Yeah.
What's the R value, the critical value for R listed for a sample size of 8?
0.707?
707. So we're going to do this problem, and let's see if we get an R value higher than 0.707. And if we do, then there would appear to be a linear relation to the problem. Okay? Awesome. Because of course, the more and more data you get, there's more opportunity for data to be spread out. Does that make sense?
Mm-hmm.
Awesome. All right, so let's find this number. But are we going to do it by hand? We're going to use what?
Technology.
Technology. All right. So I'm going to rate. Can I erase this?
Yeah.
Great job. Hey, this is kind of based on slope somehow, because positive like this and negative like this, isn't it? All right. So let's go to our calculators. And I want you to go to Stat, Edit. I want you to put these in L1 and these in L2. Sound good? Put those in L1. And put those in L2. Won't take long. I'll do it myself. I know, and you're like, hey, I could have done this before class. I actually prefer to do it with you, in case someone still forgot how to do this. I go to Stat, I go to Edit. I'm going to hit the light so everyone can see this. And I got stuff already in L1 and L2, so I have to clear this stuff out, huh? So I'm going to go over to L1. I'll hit Clear. And then I'll go to L2 up there or here. I'm not going to hit Delete. I'll hit Clear. And I'll hit Enter. Cool.
Would the
Brandon.
explanatory variable always go in L1 and the response variable always go in L2?
Yeah. Shh. Yes, that's correct. So explanatory always goes in L1. The response will always go in L2. Cool? All right, so good question. Hey, I'm going to go in here. 100. We got a 102, 103, 101, 105, 199, 105. I'm going to go over here, 257, 264, 274, 266, 277, 263, 258, and 275. Looks good. And I'm just gonna hit quit when I'm all done. So Randy, very good. Everyone, always put X in L1. Explanatory. Always put Y in L2. You go, where do you go now? Oh, I just hit quit. Remember second mode? Get out of here. Now, when these calculators come from the factory, and then they're shipped to Best Buy and these other places where they sell these calculators, the diagnostics for finding this value are not turned on. Okay? That's the default. So all we got to do is turn this on once. So can we do it together? We're just going to do this once. We only have to do this once. We'll do it together as a class. We're going to turn the diagnostic on. So how do you do this? I want you to hit second 0. I'm going to hit second 0 to get the catalog. And I'm going to scroll down to diagnostic on. So I'm just going to hit the down arrow and just go la-di-da-di-da-di-da-di-da. I'm going to wait till I get there. Diagnostic, there's the C's, it's alphabetical. Diagnostic on is what I want. No, not off, I want on. And I hit enter. And then after you hit enter, would you just hit enter again so it says done? And if anyone got confused there, call me T, I'll do it for you. Because you only got to do this once. Right? You go, what if the batteries die? I believe it's still good to go. But let me know if anybody wasn't able to do this. Cool? So now we're good. Now it can give us the R value. Yeah, I don't know why that's not a default to just give us this. You know? Alright. So we want the R value, the linear correlation coefficient. So now we go back to stat. We've got all our data in L1 and L2, true? So we'll go to stat. We're not going to hit enter because we know we just did that. Arrow over to calc. So this is new. Where have we been previously in chapter 3? What were we doing all the time in chapter 3?
One word stat.
Alright, so if you know, just a reminder for your notes, you're like, in chapter 3, we always used one variable stats. Because it was one variable. But right now, we've got these two. So if we're in chapter 4, you're going to use number 4. Let me say that again. We're in chapter 4, you're going to want number 4, which is titled linear regression. Did anyone see that? Hey, remember y equals mx plus b? Yeah, see that thing right there? We'll be talking about that in 4.2. So we're all going to hit 4. And then we're just going to hit enter. As long as we got everything in L1 and L2, that's the calculator knows to read L1, L2 right now. Cool? Hey, you don't have to do this, but everyone, if you're like, but I put everything in L3, L4. Well, then you know what I could type? I could go L3, comma, L4. I could do that for the calculator, right? And then do it, but here I'm going to hit clear. Where do I have all my data? L1 and L2. Oh, then I only have to hit stat, calc, go down to number 4, and when I do this, I just have to hit enter. Cool? Pretty cool. Did it work?
It gives me another window.
Ah. So I'm going to go to here. She's got the newer calculator. I'm going to hit this. Anybody got a new calculator? We'll talk about what you have to do so it goes on past that. Let me see. So you went here. So then you're going to scroll down to calculate. And we'll just go down to here. And we'll go down. There you go. So when she has the newer, updated calculator, after she did that, she got one more screen, she said. She just had to take her down there to get down to calculate. Who else has a newer calculator? See, they've got it too. Hey, can I hit the lights now? Because we now know R. I want to see R? 0.93. 0.938, right? So I'm going to hit the lights. We're going to start off, I'm going to put a list of questions down, everyone, and we're going to answer these. I'm going to erase this. Hey, this formula's on the formula sheet. But absolutely, you can use your calculator to find this. All right. So letter A. And what I want you to do is compute the linear correlation coefficient. All right? That means we just got to put down that number. And we'll put it right here. Everyone, does this sound good? We've got the 3 decimal places? That sound good? How about throughout this whole entire exercise, every time, we'll go out to 3 decimal places. That means after the decimal point, 3 values. All right, so I'm seeing 0.9386. 9386. I can make it 0.939.
Nine.
Good job, you're not around like that. That was good. They looked at the 6. They said that's higher. Yeah, so 989. So I'm going to put that. So R is roughly, you can put an R there. If you want to squiggle, you can. 0.939, because we rounded. And the letter B. And when I'm coming up with some questions from the textbook that are similar from 4.1, I would like you to comment on the type of relation that appears to exist between, I can end it there, but I want to keep going. Between what? What relation? Between club speed and distance. All right.
So should we say like strong positive?
Ooh, I love it. I'll just put a big long line here. And then I can make a nice statement here. This is what we were discussing earlier. What? Turn this off for now. Comment on the type of relation that appears to exist between club speed and distance. Boy, that's pretty high and close to 1, right? So when we come up with this description, there's one word you don't want to be missing. It's the word linear. We could say all this stuff like, I heard positive, which is outstanding. I love the word positive. I heard a strong out there. I love that too. But what word do we really got to hit?
Strong positive.
Linear. Linear means straight line, right? And this is how we talk in statistics. All we did was get we got this number here. So there's other things we possibly should check. So let's start out with there appears to be. All right? Yeah, that's how we talk in sets. We'll say, well, there appears to be. There appears to be. For right now, there appears to be are you strong? Positive or negative?
Positive.
Positive, and here's that word, don't miss it.
Linear.
Linear. Linear, and then we could just say relation. If you were like, can I say relationship? Sure. Can I say correlation? Sure. Relation's good though. There appears to be a strong positive linear relation from this. Isn't that cool?
You always say there appears to be.
Yeah, I think it's great. You'll notice throughout this whole course, we're going to be seeing stuff like this.
Okay.
Well, I'll be in the next trial, I'll go, we'll look at some value, and they go, this suggests, we'll talk about that.
Okay.
There appears to be. This suggests that, et cetera, et cetera. Because in statistics, we estimate. And when we estimate, but this is cool stuff. Okay, in a math course, I can find the exact inverse function to another function. Great, but you go, where are you going to use that in real life, right? This stuff, we're just estimating. And there's a guy named John Tukey. He invented the stem and leaf plot. I know, it's kind of like, things are. But he invented the box plot, John Tukey. But one of my favorite statements by him, he says, far better is an estimate to a really good problem in math versus the exact answer to a boring problem. So I'll say it again. That's what's cool about statistics. It's far better in this role to come up with an estimate. That's what we do. We estimate. An estimate to a really good problem as in comparison to the exact answer to some just boring, lame problem. The inverse function is, the cube root of x cubed minus 5. Great. What's that going to do for you, right? So that's what's cool about this stuff.
Does
We are
statistics
estimating.
always deal with linear? Doesn't it deal with curve or rate of change?
Yes.
It does.
Exactly, yeah.
It does deal with that.
Uh-huh.
Oh.
Isn't that cool? I'm going to go to C. All right. Now we're going to find the equation of the least squares regression line. I'll write that on the board, but in your notes you could put this. We're moving now into section 4.2. All right. So at this point, I just want to keep this flowing because 4.1 and 4.2 go together. He could have made it just one section. So they go together. Now we're getting into something called linear regression. Linear regression is, we're going to come up with an equation to model the data. And we can use that to make more predictions. maybe for a golfer right there, inside here, all right? So this is called regression, if you've heard that word before. You go, what is it? We're gonna come up with a function, it'll be a straight line, and it's gonna model that data. It's gonna be knifing through this data like this, like a straight line, cool? So, let me put that on here. I'm gonna say, find the equation of the least squares regression line. All right. And let's still have their formula sheets out. We'll come up with this. Who remembers in algebra? A line, the equation of a line. They called it slope-intercept form. Y equals, watch this, mx plus.
B.
You know this. We're going to get an answer like that. We're going to get a y equals mx plus b, you bet. In stats, they like to call m a. You're probably like, what? Your whole life you've been told m is the slope, and now they like to write it like y equals ax plus b like this. Okay, which one of these is the slope though?
A.
All right, so I just want to point out, everyone, as we go through here, the number sitting in front of x, they call it the coefficient. That number, and it might have 8 values off to the decimal place, is the slope. So just for a little review, before we answer letter C, we're just making some notes for like, well, that's the slope. The number in front of x, whatever comes up, if it's 2.3 or 1.8 or negative 1.2. This number, do you remember what this number is?
Constant.
It's the slope-intercept. I don't need you to be so concerned with that. We'll talk about that. We're not going to be so concerned with the slope, excuse me, not the slope, it's the y-intercept. I apologize. I put down the slope-intercept. It's called the y-intercept. It's the number where the line would actually cross the y-axis. We are not going to be so concerned with that in a lot of these problems. You know why? Do you really care what's going on when someone had a club speed of 0? Think about it, everyone. Would we be so concerned with someone who had a club speed of 0? I guess that means they missed the what? They missed the ball and stuff, right? The ball's not going to go anywhere, yeah. So that's what we're talking about. So don't get so worried. But this is the slope. Okay? Now, we're going to use the technology to get this. But before we do, how would you produce this by hand? So I'm going to go to the formula sheet. I'm going to write the formulas on this that's coming from here, how we can determine this. Because it comes from all this right here. And it comes from that R value we found, okay? So here's the formulas for it. This is on your sheet. And notice, everyone, when we write this equation, and see, I wanted to put this with other variables. We've got B naught equals y bar minus b sub 1 x bar. All right? So if you want to copy those, great. Those are available where?
Formulas.
On the formula sheet. But if we wanted to do this by hand, right? If you and I want to do this math problem and answer letter C by hand, then it looks like we've got some tedious calculations. Do you agree? I mean, let's look through here. First of all, I need to put the R value here that we had before, the point what? 99. Then I have to get the standard deviation of all the what?
Y.
Y values. I know, it's like, whoa, okay, I can do it, but I can get that. And then I have the standard deviation of the what?
X value.
X values, okay, I can do that. And I get this, and I get this number. And I can put that there, and that's the slope, right? That'd be my slope. So that'd be my slope. This would be my slope. Now, this B naught symbol, that's that y-intercept I was talking about. I'd have to take the y bar, the average of all the y values, subtract the b sub 1 value I just got, the slope, multiplied to the x bar. And we could go through that, couldn't we? You all agree? Yeah. We could spend the next 10 minutes doing all this math to come up with it. But again, welcome to statistics, everyone. This really isn't a math course. I know we do a lot of mathematics. More important to us is what? The interpretation of this, right? We understand we can do all that, and we can spend the time doing it. More important to us is coming up with this, representing it, and knowing what it means and interpreting the slope, all right? That's what's important to us. So is everyone okay if we use the technology to do this? Cool. Because I know you could do all this. You found that when you showed me last night, you could do standard deviation of a set of variables. And you could find that R value as well. Can I erase all this down here? All right. So we're going to do this with that. All right. But our answer should be like a what? Now when I use the letter you're familiar with, something like this? Do you all agree? But when you write this, and I'll put it with yellow chalk, I want you to all put a hat on the Y.
Why?
And you can call that Y hat. And the reason is, it's Y predicted. It's not really in the data, is it? It's going to be a model. So we're going to make a little line in this thing, but we're going to call it Y hat. It's got a funny hat on it. Sound good? All right, so I'll erase this. I'm going to get a little line here. You and I are going to come up with this. Again, can you go 3 values after the decimal place on every number we get? At least. If you want to go further, you can, but go at least what?
3
3
values.
values after the decimal place like I did up there. All right, so how do we do this? Good news, everyone. We just got to look back at that screen we had. So I'm going to hit the lights. It was up there. I don't know if anybody caught it. Remember all that stuff that was above the R? It's in the same button. So I just go back and do it. You might see it on your screen right now. I'm going to go back. Oh, there it is, but I want to walk you through it in case someone blanked out the screen. Do you see it? It's all in there. They like to use A. I'll hit clear though. I'm going to go through all this again since someone forgot how to do this. I go to Stat. I go to Edit. I go to Calc, excuse me. I go down to, we're in Chapter 4, so number
4.
4 for Bivariate Data. Everything's in L1, L2. I just hit Enter. All right, so let's write this out. Would you put a hat on the Y though? All right, I'll hit the light so you all can see this. Y with the hat on it, right? See, when it's an equation has to have an equal sign. Y hat equals 3 point, go up 3 numbers.
166.
166, what letter goes next?
X.
X. Plus, now you gotta give me the B.
Negative 50.
Ooh, it's negative. 55.7
79.
and a 9. Go
And a
one more number,
6.
everyone. 7.
7, okay.
That's it. Awesome. Yeah, we could write this out further if you want. If you want to go more decimal, you can. And that's called the Least-Squares Regression line.
Since that's positive and it's put the negative, would that go in parentheses at
You can do that. You could leave it like this, Randy. I was wondering if you had another suggestion. What do a lot of students like to do? I'm going to go to Holland. How do you write this?
Just
Minus.
Minus. Who else does that? Right? If you like, I prefer it too. I'm going to see, the majority class was like, yeah, a plus and negative in math, we can just write as a what? It looks better. So I think, Rainey, your idea was great. Please be able to do that. But I like that even better. We see plus now, we'll just put a subtraction sign. You know the calculator, right? Awesome. So everyone, what's this line doing? This line, it's called the Least-Squares Regression line, is a model. It models the data. And we can use it to maybe perhaps make other predictions inside the scope of data. I'm looking in here, everyone. I see 100 miles per hour, 102, 103. Everyone, I don't see a golfer had 104 miles per hour in there, do you?
No.
I don't see one with a 104. So in that case, I can make a prediction of perhaps what a 104 mile per hour club speed would get in terms of yards.
Oh, so
Right.
you just put 104 in place.
We just put a 104 in there. It'd be an estimate, but that's what we do in stats, right? And you can do this with a range of things. You look in the textbook, everyone, there's one problem where they took the circumference of child's heads and the height of the child. And sure enough, they saw a strong positive linear relation. Cool? Cool? All right. There's a bunch of others too. You know, weight of car, miles per gallon. You all understand this. The heavier the car, what happens to the miles per gallon? Kind of goes down. But these light cars, ooh, wow, you can get like 45 miles per hour, but you might get an accident or something, right? Ooh, there was a question over here.
So I just want to clarify, so that equation is showing that was the linear relation, correct?
That's right.
Okay.
That's it. This gave us the strength of the linear relationship. Now this is going to be a line, we're going to draw it, that's going to go through these dots. And right now you might go, well, I'm just going to draw a line like that. But I say we use the calculator. So let's go to the calculator. Let's see how this line looks. It should cut right through those dots, right? So, where do I need you to go? I need you to go to stat plot. Top left corner, let me hit the light. I'm going to hit enter. Now which one of those looks like a scatter plot?
The first one,
All right, so would you go to the first one and hit enter? Remember when you hit enter to make it lock? Now watch what happens when I hit enter. Watch these change. The calculator, it's a smart calculator, it should know to read L1, L2. So I'm gonna hit enter. Ooh, thank you. Now mine didn't do it. Did yours do L1, L2? Mine, I did this on purpose in the class. I'm going, wait, I want L1. So all I have to do is go down here and change this to L1 off my front screen. But yours, I'm sure, automatically did that. I made it do that, because I like playing around with the calculator. I'm like, oh, I gotta fix that. Now, do you remember the zoom what for stats?
9.
Zoom stat is zoom 9. That's gonna give us a nice image of this. All right, so we're gonna do that first, and you're not gonna see the line. And so I just wanna give you a heads up. We're gonna do this. All we're gonna see is the scatter plot. Zoom 9. Ah, cool. That's what we got before. How do you find these numbers though?
trace.
All right, Owen, I want you to hit trace. It's right next to zoom. And you can move around. Does it work?
Yeah, I can go for one screen.
Oh, okay. I'll come over there if you need some help. And I'm getting all these. Want to see all the numbers? But you and I also want to see the what? The lines. So this is simply what we have to do. We haven't gone here yet. But you've been in algebra courses before. I'm just going to hit y equals in the top left. Not the step plot. I'm just going to hit y equals. And I'm going to manually type in 3.166. Does everyone know where x is? X is right under mode. I'm just going to go to y equal. Just type this in. And then there's a minus. And let me see where the minus button is on the right side, right column. 55.797. And then I'm going to just hit graph. I'm just going to hit graph. Ooh, there it is. So I'm going to do it with my yellow chalk right now. I'm going to go like this. It came off here. It looks like right near that dot. And it cut through. Right there. This is called the Least-Squares Regression line. I think I'll hit the light. And I'm going to label this. This is called y-hat, right? So Liz, this is the y-hat. And it's some model. Go right there and I'll put it. This is the y-hat equation, which is 3.166x minus 55.797. Cool. What's it for? Well, we can model under data. This was the real life data. Maybe you and I can make some predictions. Hey, I rarely see students do this. Okay? I rarely see students ever do this. But feel free to talk like a statistician. And write like a statistician. And when statisticians aren't really mathematicians. So you know how they like to write this? We got y and an x there. They like to put the words. You know what y was? Distance. So they would write this like this. Distance. And then they put the hat like this. Equals 3.166 times, what was x? Speed, okay, speed. Put a parentheses around it. Minus 55.797. Now, do you have to write it like that on a test? No. And I'll tell you, when I've graded tests for years, 99% of students like to write like this. That's how they've been trained. Plus, they find it easier to write y than this whole word distance. They find it easier to write an x, but statisticians like to have the words there, so when they plug numbers in, they're like, oh, if I plug a number in here, I'm plugging in a speed here, and it will report to me the what?
Distance.
The distance. So if you want to write like this, absolutely, just make sure you put a hat on that guy, right? Put a hat on that thing. But yeah, when most students, I grade tests, the answer looks like that. Cool. All right. Hey, I'm gonna erase this. We're gonna go to letter D. And the next thing we're gonna do, Owen, is interpret the slope. Interpret the slope. So we're not just going to write down the slope. You and I are going to interpret it. All right? We're not just going to write it down. We're going to interpret the slope. We're going to talk about what it means in terms of this real life problem. All right? So first of all, where is the slope?
3.166.
3.166. Everyone remember this is the slope? That number, we got to talk about it. We gotta put it with words. It means something. So, see this line here? When I'm gonna go off this line, I'm gonna draw a triangle. Really small, but then I think I'll go over here, make it bigger, and then you and I are gonna put words to this. We just gotta talk about this. Have you ever heard rise over run? Okay, we gotta talk about this rise over run in a sentence. So over here, it's like I can make a triangle, maybe right here. You go this way, and he goes up like that. Okay, there's my triangle, but I think I'll draw it bigger. How about right here? Shh. Shh. And what I'm saying, everyone, every time I go 1 in that direction, it appears that the line went, what's the slope?
3.166.
The line rose 3.166 notches. That's what appears is happening. Okay? So every time I go 1 this way, the line is going up 3.166 this way. Right? Now, I need some words. What's 1 what? What is that word?
To the right.
It's, what's the variable? So we gotta get these words in here. All right.
Speed.
1 this way, 3.166 this way. We gotta talk about this somehow.
So for
All right, this one, what is it representing? The
speed.
speed. What's the units though?
Mile per hour.
So I'm thinking, okay, for every what? 1 mile per hour in the speed that I go this way, it looks like that golf ball was traveling, what? 3.166 what?
Years.
Oh, I like it. You went back, you're like, what are the units? Yards. And you and I have to just put this in a sentence. This is what we're going to talk about in a sentence. I know we all can do that. Can everyone see that? I'll put that triangle again right here. We're going to put this in a sentence and talk about this image. You know, 1 mile per hour this way, 3.166 yards this way in terms of this problem. Cool?
So can we write like 1 plus?
I like that. I know, that's only one thing about stats, and we do have to discuss this stuff, right? We'll use the technology to facilitate the mathematics, but we get to talk about this. All right. And before I was saying, Randy, there appears to be, you watching here, we can use words like roughly, you know, because this is an estimate. All right, interpret the slope. Here I go. And I'm going to talk about that right there. For every, I got to use the word increase, though. Would you agree? For every increase, of 1 mile per hour in speed, so I'm going to erase this image, I got it over there. For every increase of 1 mile per hour in the club speed, or the club head speed, comma, now I got to talk about the y variable. What's the y variable?
The distance.
The distance.
Increase.
And now I'm going to put a word in front of distance if you don't mind. Oh, this thing had a hat on it, right?
So estimate.
Right, I'm like, okay, there's a y hat. The estimated distance. I'm going to use that word. This is called y estimated or y predicted. You can use predicted distance. I'm not going to mark off, Randy, if you just said the distance, right? Because you're talking about that line. But I should use this word estimated because it was an estimation of what's going on. All right. So for every increase of 1 mile per hour in the club speed, the estimated distance will also increase. How much? I love it. And when you're not using that number, where are you?
No.
Don't look at that negative 55.797. You're saying 3.166 yards, right? Let me repeat this again. You can use this as a template. You could do every problem this way. For every increase, you can always use 1 in that direction. Because then when rise over run, we're saying rise over run. For slope, you've heard that before. The rise is 3.166. The run is just a what? 1. So you go, oh, can I always use a run of 1? Sure. Sure you can. Right? Is that okay with that? T, you're it does? So it's like, all right, for every increase of 1 mile per hour in club speed, the estimated, there's my y variable, will increase 3.16. The key words are these words increases, right? So and before I go on and do a letter E, I want you to be exceptional at this, especially in a testing scenario. So can we talk about how would you write this out if the line went down?
Decrease.
All right? Ooh, that's good. So let's make an example, everyone. We'll go off to the side in our notes. I know this is letter D modeling this. Can I erase that? Yeah? All right. I'm just going to go off to the side and let's just pretend right here, and I'm just going to make something up. Because I saw something like this in the book. Ready? Let's say you had this. Y hat equals negative 2.3x plus 93.1. All right? Let's just say you had that. Y hat equals negative 2.3x plus 93.1. And you go, what is this talking about? What's the relation here? In this problem, everyone, x is, you're going to laugh, the number of days absent for a student. All right? So x is the number of days absent. The y is the student's grade. I'm writing this kind of low, so I'll make sure when I repeat this, everyone's going to hear this. In this case, I'm just making up a little example right here. Let's say x is the number of days absent for a student, and y is the student's grade in the class. And someone looked at this relation. How did students do that showed up to class all the time, and some of the students that missed like 15 days? And someone actually saw a linear relation in one of their classes, or just a bunch of classes combined. But if you and I had to interpret this slope, we notice it's what? Negative. Now, do you agree that means the line would go down this way?
Mm-hmm.
Yes.
Now, the good news about the triangle is you can still run to the right. You can still run to the right, okay? You can still run to the right. So when I start out the problem, now when I'm going to interpret, can I erase the top part?
Mm-hmm.
So we'll just interpret the slope for this one. I can still start out with this for this problem. I'll get this out of the way. I'll get all this out. Interpret the slope for every increase of 1, but what was x? What was x in this problem?
Negative 2.
There's our triangle. We're like, this was 1, but x was days absent. So when this is 1 day absent, I got to talk about this slope. For every increase of 1 day in absences, or you can just say 1 day absent, for every additional day that a student's absent, the estimated, what word?
Grade.
All right, student's grade. I like it. Student's grade. For every increase of 1 day in absences, the estimated student's grade, what does it do though? See?
Decreases.
There you go. I can't say increase. We all know it drops, right? Do you want to use the word drops? You can. But I heard decrease. I like that word. Will decrease, how many points?
2.3 points.
Decrease 2.3 points. Does everyone follow me? So that's if you want to practice some problems out of the book and you're like, oh, but the slope's nice. All right, that's how we interpret. And welcome to statistics. This is what we do. We use technology, absolutely, to facilitate the tedious calculations to come up with this stuff. But you and I discuss this in terms of our problem. So if you go out and do your own real life problem, you can do the same thing. And we talk about what we have, but sometimes we got to make sure, well, is my R value good enough? Is my linear correlation good enough? Cool? So when we got out to letter D, next class, we're going to move beyond D. I'm going to do another E and an F and a G and an H and all that. Does that sound good? Hey, have a great weekend. Super job today.
Test is on Thursday, right?
What's that?
The test is next week, right?
That's right. And if you look at that, remember we have to move every test back 1 day? So, Liz, the next test is
Thursday.
Thursday next week. Cool? A week from today, next test. Only goes up to 4-2.